So please open MobiXterm and just follow what is on this pieces of paper, and I will instruct and show, but if you feel comfortable reproducing the figure, you're fine. So I will go around and distribute things, but I have also sent these things by email. The plan is very simple, very clear for today. We give up attempts to connect to CCast for a short period of time and just learn how to process the calculations that we did last time. Okay? So it took maybe half a minute, but we didn't open all power of calculations that you've got. So last time you have learned how to extract total energy, right? And we did simple titanium hydroxide, right? We also discussed a question of color and gap between HOMO and LUMO, highest occupied, lowest unoccupied. And today we, I think it is most easy and pleasant part, although it's not like relax and do nothing. Like often invite you to relax. No, now please get involved, and it will be hopefully pleased. So we'll get the concept of density of states, molecular orbitals, and we plot about 6 orbitals for this titanium hydroxide, and I will guide everyone step by step. By the way, please download, install MobiXterm, connect to Photon. We'll do. And as soon as we get through this material, I will invite you to repeat the same step, density of states and several molecular orbitals for another few models. It was extra credit homework previously to build this model. Now, I would like to assume that you have done it. If not, just quickly build. Building of models is not, there's no time. So, cesium 4, lead 1, bromine 6, and the model with dimer of titanium hydroxide.
And you just want us to do energy calculations?
Do single point, like optimize with Broom. No, do not waste time on true optimization.
Okay.
And then do single point Hartree-Fock, and then repeat all the steps. Okay? And I'll guide with everyone with tiny details for the first time, and for the rest you will be more on your own. Okay? And there will be lectures next week through online connection, but there will be no lab. So I'll try to please you with some long homework or 2 homeworks, right? But they will be based on important and interesting things. It will be not pretending that you're computers and optimizing geometry by pen and paper. Okay, so please make sure that you are logged into Photon, where you have single point. And I will do the same. Yes?
Do we need to log into yours?
The one where you did the titanium hydroxide single point job.
Okay.
And I think all of you have completed it, right? So let me share. So you know what to do, right? Do not expect too much organized instruction, although I will try. So let me share. Maybe right now it is a good time. Suggestion, piece of advice that I didn't follow for today example, but for the future, everything you do computationally and especially for the projects, try to open new directory for each new job. Right now, when we do practice Gaussian software, it's not critical. If you do it just for entertainment, it's also not critical. Gaussian use unique names for each job. But very soon, when we will be using different software, the names will be standardized and they will override each other. So it will be assumed that each job is running in a separate directory. And start thinking on your background, how you will name directories and make them in a system that you are happy with. Yes?
What's the password for the CHEM676 account?
Anyone remembers? No? Okay, I'll check it in the mail. It should be the same like CHEM476 _ star, something like this. But huh?
It's CHEM_476_2019.
Make sense? Good. I should have put microphone on mute. So in your directory, please find out the file, log file, that contains successful outcome of the single point Hartree-Fock calculation. Last time we were discussing the content of this file, right? I'm going to bring just navigate to the same place where we stopped last time, right? You remember these tables for occupied and unoccupied. So I'll just make a circle and see that everyone has access to such file. in, but it would be great to have calculations for titanium hydroxide like we all did.
Alright. Yeah.
Okay.
I'm looking for it. I'm just trying to remember it. Give me a few minutes.
Yeah, I'll make a circle to make another stuff.
That's the username.
No.
Why?
The password doesn't work.
Okay. Steven, did the password work for you? Okay, so can you talk to each other? Like, can you approach and help? Them?
No. I figured it out.
You did? No?
Yes.
Oh, okay, thank you for being ready to help. Oh, yes. Oh, no. This is.
This is a TI. This is pretty safety. That's right. So
That Oh. Okay. And
So that's
if you
great.
can follow the instructions.
I can help you now.
Oh, really?
Oh, really? Well, because what I scribbled down, you probably typed that one.
Gentlemen, how are you? Yes, good. You can change it. And, nation.
Hello, you did? Yeah. Push the button and everything else that way.
Oh, yeah. Did you get it? So you got this right there.
I can't remember where I put it, unfortunately.
Okay, that's good.
What is he missing with TI? Because I'm gonna, so this was his personal, because, and then they made this one for that. So if you want to go into this one, that's where we made the TI one.
Will you look into this account?
That's the,
No, I'm logging into that.
What
Your Proton account.
Did you complete the domain base? I don't know if you did. Okay, that's just probably more. But you need to be able to. Next assignments will be able to do this.
Okay.
So, everyone get access to this log file?
Not yet.
Not yet?
Look, well, I,
Yes. And we do everything in the command line, right? That's fine. We're going to process. I just see something what you're doing. There is a suggestion, please. Well, I don't care, but for your own benefit, try to avoid spaces, dashes, exclamation signs in file names. Try to make it continuous symbols or numbers. Otherwise, in Windows, or Mac OS, it doesn't matter, but in Linux command line, it's really hard to put a space.
Yeah, and you have to do like a
Apostrophe
Right.
or
Yeah.
backslash, and it's very irritating. So lift hands who doesn't have access to healthy log file.
So, you're on.
And should be have all of this.
Well, hold on, we're on two different accounts here because your personal one should be low,
Oh.
but then this one's capital.
No, it cannot be.
Because we were both locked on.
Maybe you just run it through, it's not so case sensitive. The first series.
That's not working. Where is it?
Yes. No, you're ahead of everyone. Try to build two other models. Yeah. Yeah. And it's very encouraged to help each other with chat. So there are no secrets. You're not competitors. So if you already some of you went ahead and completed building the figure. If you did, if you have free time, try to build two other models.
Yay.
Okay, so let me, if you are comfortable going forward, I'm very supportive of that. But if you need a little introduction and instruction what we are doing, let me quickly
That'd be
go
nice.
through. So you see, even this little molecule that has how many 9 atoms, and we reduce basis set, we do not consider core electrons. Still, it has so many orbitals, right? And we will go over what are these molecular orbitals in the class. It will take time to define them rigorously, but it is the electronic states which electron may or may not occupy, right? So we are humans. We are much smarter than any computer, but we cannot meticulously go through large number of numbers, right? So we can focus on virtual occupied, maybe like a couple of numbers, convert them in different units, analyze. But if there are like 100, it's not comfortable. Yes?
How do we get the band gap energy from that?
Same as last time?
Just subtracting the.
Yes,
subtracting
and
the-
convert from atomic units to
Okay,
electron volts.
which subtract what from what? The
Highest from lowest,
highest from lowest. Okay.
right? So we need a tool that will represent, so we need to characterize material. And this is excessive amount of information. We do not, it's not human nature, and it is, we do not need so much information. We need just basically assess what is the gap, how dense states are, some very simple. And we need a way to convert this large number of numbers into something that we can comprehend, right? So the suggestion is to use so-called concept of density of states. Please leave hands who is comfortable with this concept by now. 1, 2, 3, 4, and half. Who is completely not comfortable with concept of density of states? 1, 2, 3, 4. Who is like in the middle? 1, 2, 3. Okay, so I'm going probably to so we do have energy axis, right? And we do have numbers. So about minus 13 electron volts, about 0 electron volts. So we have levels, right? It is what these numbers tell us. We can convert them and draw lines corresponding to different energies. But if it is more than 5, a human brain doesn't perceive it or resist to perceive it. Why don't we design a special function which will split this axis onto the intervals and measures tell how many energy states is in this interval, right? So if we are in so-called gap range, then this function will show 0 because there are no states here. If you come into the region where there are states, it will be more than 0. So we can, like here, if you put same energy axis, there will be more than 1. Here, maybe a little less. Then it will be lower density, maybe then higher. Then here it will be 0. About this energy, it starts having some non-zero density of states, right? Are you comfortable with this diagram?
So it's the number of states per energy level?
Number of, no, per energy interval.
Okay, per energy interval.
Per energy interval. So we split the whole energy axis on intervals and then make a function that shows how many states per energy interval. So if we want to be rigorous, we can tell dn dE, number of states per energy interval, right? As function of energy. Good?
DOS acronym is what?
Density of states.
Density of states.
And the states are the intervals.
Right. Huh?
The states are
States meaning
intervals.
energies of orbitals.
You say this.
Density of states.
Oh, yeah.
States. Not
Yeah.
like state of the art or state
Yeah.
of California. Energy states.
So DOS is the interval range?
No, it's number of energy levels per energy interval.
Got it. Good.
And we can put it like delta n divided by delta E if you want to be discrete. We count 1, 2, 3, and we will take 1, 2, 3 levels per this energy interval.
Thank you.
Good? This is rigorous, but it is not comfortable. Right? Because it's ugly steps. There is a way to convert discrete list of energies into nice continuous density of states. This is definition, but in addition to this definition, there is a pretty trick that makes nice figures for good publications. So we are going from discrete to continuous. Continuous. So we can make a convention. We can make a convention that as like we are going to scan the energy range, and as soon as we have a level, we will put a little spike with some width. If you are really meticulous and curious, you will ask like, what's the reason for the width? And you can tell, okay, thermal fluctuations, because energy can be a little higher or a little lower because everything fluctuates. As soon as we see another level, we put another peak. And since I'm just lazy to go over the whole interval, we add together this function. So when we add them together, the resulting function will be like a little higher. And if two levels somewhere else will be really close to each other, then these two functions will coincide and which will just double how high it is, right?
So we make this continuous by decreasing the size of the energy intervals until they get all the way to zero? Until the interval is
The
zero?
energy intervals will be considered infinitesimal,
Okay.
really small. And this procedure of adding spikes, so each spike can be formulated as a Gaussian function, energy state number I, minus energy, which is our continuous, square some width parameter and some normalization. So this will be a function for one spike. But if you have many spikes, many energies, you just put summation over I, where I runs for all energy states that we do have. And this will be, we can call it dose of energy. So this energy without index is a continuously running variable, right?
So are all these spikes delta functions?
Yes. Summation over I, delta E minus E sub I.
Okay.
But delta function, more rigorously, delta functions, but can you draw delta function? It's infinitely thin.
Mhm.
And everything we do by, like, even the pen has a finite width. So
Right.
if you want to see it by our eyes, we better assign artificial width,
Okay.
just for better visualization, on one hand.
Mhm.
On another hand, we are not in math, but we are in physics or chemistry. So, and there is a mechanism that brings a little fluctuation uncertainty to the value of energy. And we can assign it to here. Make sense? Okay, so this was a little introduction, but how can we get through practical part of this? Are we still on record? Yes. It's not yet muted. So if you look through this little memo, you will see instructions, same as on the board. And let me make sure that they are also available in this CHEM676 as well.
I do not believe so.
I'll make sure that they will be there. It's not a problem. And give me a couple of seconds, and it will be there. Well, I was lying. Maybe a minute. Okay, so if you look through this advice, DOS goes, it's just a little memo, same as in your printed copies. So there is a script located right here that, like if you like programming, you can look inside, but it does nothing but grabbing, parsing write lines from this file. So you remember, let me go to a different screen, that there is a segment of the file that contains energies. And in order to practice this definition of density of states, we need to list them, right? We could do it manually, putting them into Excel sheet, but it would take a long time. So we need to just read them and write in a column. So the script is instructions what to do, but actual thing that access the CPU is Perl. So for the Perl, so to say, language, you put space and then name of the script, then space, and then your .log file, which means output of your successful Gaussian calculation. If you will do not copy literally what is here. Each of you have designed your file individually, like titanium hydroxide or titanium 04H4, or maybe you put something creative. .log and then space. And then there are 4 additional arguments. So if, let's look on this little definition on the board once again. So we do have axis of energies, right? And we have about 100 orbitals, maybe here 50. But if you want to represent them continuously, we may want to have more than 100 steps. So we need to split energy interval on relatively large number. And it should be general, it should work even if we work with a system with more energies. So good number will be 1,000, 2,000. If you go too much, your files will be bigger, and resolution of screen, even if it's 5K display, doesn't have more than 5,000 points, so there is no reason to go to too large numbers. Right? So the next is parameter that defines the width, artificial width of the delta function. We can put it 0.1 electron volt, but you have, later on you will try to play and see how the shape of the density of states changes if you modify this number. And then another 2 numbers, which in this template are 5 and 5. For titanium hydroxide, try to use a little bigger number, maybe 10 and 10, but you're free to modify these parameters. It is how deep below from HOMO and how high to the top from LUMO. So specify the energy interval where you plot your density of state. Okay? So, yes?
What if we want to zero it? Get our
Later.
Okay. Sounds good.
Okay.
Yeah, I'm not here.
So Perl bin cap PL. Oh, before I do this, I make a copy. Yes, I will approach you in a second. Well, I'm lying. Not in a second, but very soon. So when you, upon you hit enter, here is an example what it should type you. So let me walk around and see if you get things similar to this what is on the screen. Enter. Good. You don't need to.
Yeah, I was trying to edit to get this.
No. Just hit enter. Hit enter. Looks good. Looks good.
Did you just want us to practice with the
This?
changing those?
These were not part of the instruction, this could be just explanation.
So we're supposed to do for one column this here.
It will be just a little worse or a little better.
This line is going to be a correction of this line.
Is it the same?
Good. Okay, so upon you complete this step, there should be a couple of files. So let me attract your attention. You will never need them. It is only for curiosity. So e sub oc, e sub virt, e sub the name of your file .log, and then DOS. So first two files just parse blocks of orbital energy from output of Gaussian, right? So if you type more e sub oc, you recognize this alpha occupied energies in atomic unit, right? If you type e sub virch, it gives the list of orbital energies in atomic unit, just part of the .log file. Then if you look into next file that has been created, it includes list of the same files, but now they are converted from string to column, right? And they are converted from in fact it contains both atomic units and electron volts, right? So if you scroll a little bit further, you will recognize these two numbers, minus 0.5 and about 0, which corresponds to gap. And here it tells how many electrons reside on this orbital. By Pauli exclusion principle, you cannot put 10 electrons into one orbital, but you can put 2 because they have opposite spin. Right? So where you jump from 2 to 0 occupation, it is your Homo-Luma gap. And here it is in atomic units, here it is in electron volts. So last time we suffered a lot by using a calculator to multiply this number by 27.12. And here it is done automatically. Right? Electron volts, there are no rules to do everything in electron volts, but different communities prefer different units. For these calculations, they are quite reasonable because like 2 electron volts is optical range. So if you have few numbers, it means you are in optical. If you are substantially less than 1, it will be infrared. If you are substantially more than 1, it will be ultraviolet. But there is no, if you want to convert it in other units, be my guest. Okay? So now you do have a list of energies, and they are arranged in a convenient way. Now we need to convert this discrete list of energy, discrete list, into continuous function. Continuous in numerical sense. Function that is represented through like 1,000 or 2,000 grid points. Yes?
So like a model from the data point?
Please repeat.
Like a best fit line from the data points?
No,
Kind of what you're
no,
saying?
no. I do not know how to explain. I can just, in a civil way, point once again on this equation. So we are practicing this equation. So list of discrete set of energies is converted to continuous, nice looking shape which of density of states. It's not fit. It is special definition where energies are dense, density is high. Where energies are sparse, density is low. You cannot call it fitting. But it's analogous to fitting only in the first 3 words. Converting form. Continuous into discrete into continuous.
So the more dense an energy interval is, the more likely that energy will occur?
Oh. The denser energy states are offset from each other, the higher the density of states. The interval of maybe you wanted to say this, I misinterpreted it, but there are two different things. Density of grid points, which we define as humans, and offsets between energies, which is computed by the software. But this offset between energies is very special and very different for each orbital, for each energy. Therefore, if they will be offset by the same number, the density of states will be constant line, constant. But they, as you see from images, it goes up and down many times. Make sense? So this operation has been already completed. Minus LT. So if you look on the last file that has been created, it has DOS underscore something, right? Underscore width parameter 0.1. It is stored here just in case if you decide to redo density of states again and again with different parameters and compare them. And if you look on this column number 1, 2, 3, 4, 5, column number 5, you see that the size of the file that starts with DOS is substantially larger then list of orbitals. So list of orbitals is 3 kilobytes, and this one is like 170 kilobytes, 168, right? So because we inspect range of energies with denser grid points. So let's look inside this DOS file. And by the way, for the sake of future use, if you see this instruction, it is reasonable to rename it in more standardized name. Let's rename it into the dos.log. Yes.
I forget, what does the U1:2 mean when you have it on your DOS figure?
Using first and second columns.
Oh, okay. Okay.
We'll get to it very soon.
Okay, sounds good.
So, DOS score. Oh, let's copy. Copy. DOS underscore test into DOS.log. More DOS.log. Screen is not broad enough. So it has a couple of columns, and they include energies in electron volts, and second column includes density of states, which you see it changes slowly and continuously, and there will be non-zero density of states even at energies which at which there are no energy levels. So it kinds of making smoothering of this dependence. But if we drive to the range between 0 and -13, so we used to have some energies close to -13, but if you go into the null region, into the gap range, like -12, it will be very close to 0, 10 to -9, right? Or 10 to the minus whatever, 20. So it's as good as 0. And if you go to 10 to the minus 100, and if you approach the energies of the LUMO, about 0 electron volts, it starts growing. So like 4 or 6, right? I'm not sure if it is normalized well, but one can normalize it in such way so that the number here will tell approximately the number of energy levels in this region. Okay? Let me walk around and check if anyone has questions.
Yeah.
So try to look in these files if you have curiosity, but the main thing is to create figures. Please.
Yeah, that's where I'm reading.
This one is offset. Same forces. Only the same as the first one. And here is totally different normalization.
So all of those
Space. It's space.
CP is what, copy? Or what?
Yes. You were able to.
So I just copied it, put it in this file. So the
Yes, you're doing this.
CP side, what is it?
Oh, it's
Okay.
okay.
He gave that.
So you don't literally have times. You take your file.
Okay, so do we go to this line next, or just go to this Orbital or to this?
Well, it's either this. Well, I give
Oh, so
two
that
examples.
means the, okay.
Okay. So if you see this instructions, once again, more bin advice DOS goes. You see the next instruction. So what is this command? Anyone wants to suggest? Yes, yes. So we are so modern. Everything works so nice with touch screen smartphones. But a lot of scientific tools were designed, like you cannot imagine, like 40 years ago, when there were no graphical screens. Everything was like almost as like typewriter. But people needed graphs. So there is a command line operated program to make graphs. And here is one of them. So what this software does, I'm not sure about 40 years old, but 35 at least. It also, as any command language, it uses a script. So if you look inside the script, it will show some instructions. So it instructs to plot file named dos.log, which we just looked through, using column number 1 as x-axis and column number 2 as y-axis, right? With lines. And if you do not believe me, you can do man space GNU plot, or look for GNU plot in the whatever online. And the rest of things are just little icing on the cake. So putting labels, giving. So unlike modern drawing programs, it doesn't show anything on the screen, although it can. But in this mode, it doesn't show anything on the screen. It forwards the graphical image into file dos.go9.ps. So there are PNG, PDF graphical files, and one obsolete format that we do not use anymore is PostScript. It's an ancient graphical file. But in the next line of instruction, you will convert it from PostScript to modern PDF. And some of you have already completed it. Okay? And here, we like nice figures with thick. Criterion of prettiness of scientific figures is thickness of lines. Thick lines means nice figure because everyone can see it. So thick line, large fonts, print. So what we do, we just practice this GNU plot of this little script. So it goes really quick. And if you inspect your directory after this, you see this dos_go9ps. Do not try to open it. We may not have right software to look on it. But it is graphical file. And it is much smaller, about 5 times smaller than data file, because it uses some tricks. When the computers were not powerful, people were designing tricks. So now we need to convert it into modern format, which is just one line, PS to PDF, write. And then DOS underscore G09 PS. So 2 means not number 2, but 2 like convert to the next format. From PS to PDF, write. So if you practice listing of your files after this operation, you see this DOS G09.pdf. It's even smaller file. So there are some smart algorithms how to condense graphical images. And this file needs to be transferred from the outside computer where calculations are done to your modern desktop, laptop, or smartphone. So try to bring it to here. How do I do it?
WinSCP.
Yes, if you know how to use WinSCP, please do. There are some ancient ways. Just SCP. SCP. Start with PDF. So if you see, you can navigate. I have opened another window. There I didn't log into remote computer, but just navigated to desktop, and then I practiced secure copy command from user, remote computer, directory, and then I instead of giving the full name, you can just anything that ends with PDF space period. Enter, then it asks for password, and then it, well, actually here it wasn't asking for password, it remembered it, and it transferred the file. After this, I look into the file manager, into like desktop, and there is file that has been just transferred. Let's open and see. It will be an intrigue for me. It's pathetic to wait 1 minute for a 6 kilobyte file. Not responding. Okay, is there other way to look for it? Oh, okay, finally. Yes. So, you know, computers are so powerful that companies need to design more and more applications that will use all this power for some non-important things. So, here is our density of states. This near 0, it is unoccupied orbitals. Here near -13, occupied and below. and this region is a gap, right? So what is the benefit of this figure? That it converts list of discrete orbitals into something continuous and relatively simple that human can analyze and get idea of the physical and chemical properties of matter, of molecule or material or a structure. This will become our language. So for any model that we consider in the class, we need to make this density of states image. I'm going to make a circle around and see if you got it. So for your future homework assignment, which is unknown for you, but there will be one, please try to copy this image and put into either Word or PowerPoint. Did you get it?
No, can you remind me how to get out of this?
Quit or exit? Just try.
Well, not doing, because isn't that his file?
Yeah,
We exited everything and now
That's X. Yeah,
it's coming.
Wow, that's pretty cool.
Good.
Oh, I think so let's
Well, I think it's trying to access older power. We have to declare what it's accessing to, where it's going to access. And then it's going to send it. Oh, maybe. Oh, if he's sending it to his computer, then maybe send.
Oh, that's great, that's great.
Oh, yeah, that's what we're saying.
Oh, you don't know what is a local computer?
Yeah.
discover ways to convert logic to PDF.
We were just trying to figure
That
out.
is what's in this file here.
Yes, this steps are more complicated than actual operations.
Right.
So,
Right.
Arrow up, space, space, keep space. Period.
Hold on.
No, type the password.
This is the contents of the file.
I didn't send the
That type the password. Your favorite. Yes, yes, yes. This one.
He just kind of wanted to look at that.
For you, if you use here,
Because now,
Okay, no such file written. But
Okay.
that's because I messed up. Right.
good. Come on.
Smart.
this has
Mary, can you help me for a second?
Sure.
Okay, so this is my PDF. How do I open it?
Oh, you want to transfer it to your desktop? Are you on desktop?
No, I didn't get my killer photon.
Okay, where's your desktop?
my understanding is he just wanted.
So you want to do it SCP, so you want to get, you know you have to do it in, desktop. Because you're copying stuff from the company. So you go to, SCP.
I'm not responsible for the speed of show. Okay, now you can.
So basically,
Yeah.
Okay, so SCP, this whole thing.
and then your stuff, and
Alright, and so that, and instead of this asterisk, I put the name of my file.
you could put asterisks, because it'll just like, so that's fine, you just like.
Alright, thanks.
The same so it creates. They don't want to using one is say energy. And the other is densities. Cool. Yeah. Which is from the log file named gas format. Let's go to that discipline. No, this is just kind of a breakdown of what these things This CD's machine on the CG copies style commit to file beginning clock is expecting this file to get this is secure copy. So you need to write this space on each of the settings. Okay. That's what it is.
It tells you what is going on with So because I was logged in, CHEM676.
Did you get it?
Just
Did it work great?
What's I gonna do with this check mark?
Oh, cool.
Where do I find this?
Yeah, you're in your desktop, right, so get out of here. Well, actually, go
Everyone is happy with density of states? Yes?
I'm actually doing, if I want to get like something like binding energy or anything like that, does that relate to these states?
Not yet, but we will do it.
I was,
For binding energy, you need total energy with and without adsorbate. Right? Binding energy is single model calculation is not enough.
okay.
You need to put something in and out. Right?
Okay.
Other than that, everyone is happy, right? Please review the protocol and attract my attention and ask, because I promise homework will include making like 20 density of states, or maybe like 12, but substantial number.
Can we save like these two? I mean, I'm okay with the whole trial and error. Can we save this? How do you say, whatever interface we're looking at, can we save them somehow, like as if it's like a project we're saving? So I can look back and be like, oh, I messed up my code this way, or
Can I have your help? We can do that.
Yes. What do you mean save?
yeah. So like, I mean, this brings today's been very valuable just because we've done everything and more, and so I didn't know if we could.
You can copy everything and then put it in your Word file or whatever. Let me share a thing that is not very comfortable right now, but for the future. So Mead wants to save your step-by-step things. Right now, we are using the same common directory, therefore it is not as useful. But generally, if you use personal account, you log in and log out. Then at the instant when you log out, all your steps are stored in the file named .history. And it accumulates for substantial number of steps, like 1,000. Like if you are, well, right now we are trusting each other and using this common account, but typically everyone has a personal account that no one else can see except system administrator. And then system administrator can check what you are doing at your time, looking at a history file, and each step you are doing is stored. Right? Does that answer your question?
Yep. Yes. Yep.
Okay.
Okay, so I use the scp command to put my PDF on the desktop, and now I can't find it.
Okay, let me.
Very good.
So where your car?
I'm not responsible for that. If your file is healthy, it should be healthy.
CS4, EB, BRS, so go to GView. EXE, let's create this.
Oh, it was too short.
What?
Here, PS is empty.
Alright, so which command did I miss? Was it like this one or the one below it?
Okay, I've got a question I'll answer to everyone. So let me, before we go to the next chapter, let me summarize some common errors. Scientific parts were so easy for everyone. Most complication was browsing directories on local computer. So each year systems are changing. Things that we do on clusters are stable, but systems are changing. So if you are in MOBA Xterm, let me open another one. So you check where you are, PWD. You see that you are in MOBA Xterm, right? And you may not sure where it is. So going one step up, PWD, home, LS, and you recognize here the, well, each of you will have different name. It's name of an NDSU account with which you have logged in. So go to this name, LS, and you see there like desktop and my documents. So go to desktop, CD desktop, and then you practice SCP from remote place to here. And then after you practice it, your new files in File Manager will appear on desktop. Please do not hesitate to talk to each other. Some of you may have found much smarter ways, either installing or running WinSCP. It's a really good tool, encouraged to use. Or in your MOBA Xterm, you do have right panel where you can navigate to this panel, find your name, and find the right file, right? This will be a little quicker, but sorry for showing you the longest a little earlier. Sometimes MOBA Xterm can be unavailable. So let's be independent on availability or not availability of this modern mouse operated things, right? So if you bring it up, it pops up, okay? Makes your life quicker and easier. Yes?
For running single point calculation, you just need to specify the check. You don't have to worry about shared processors, none of that stuff.
Correct.
Okay.
I have intentions so that all of us run things on CCast, and you all are encouraged to request account on CCast. You need it. But I was checking and planning to make today's lab on CCast, but it had some issues with delays. It was not as quick as we need.
What about nursing?
For VASP, yes.
Oh, okay, gotcha.
You all will be provided with accounts on National Supercomputer with Department of Energy in about a month from now, after we finish with Gaussian. Okay. What?
So you wouldn't be able to do Gaussian there, you can only do VASP?
Gaussian is crazy with legal issues.
Oh.
More than VASP. Every software has some limitations.
Gotcha, okay.
Good. So next, any questions? Please make sure that you will be able to do this density of states image for any model. Single point, output file, copying, just following the protocol. So I'll stay here and answer questions anyway. Here's the second part of the file that was distributed. So this is most pleasant, one of the most pleasant part of the course. That can be instructed to anyone. You do not need background to draw these pictures and enjoy them. So it's many people. There are two reasons why people often select computational chemistry. One, because of drawing of orbitals, another because of finding normal modes. So please look on this second page, and the goal is to get images like the one here. Okay, so I'm not providing definition. It's not very complicated thing, but we need a couple of class hours before we get through formal definition. So the molecular orbital and multi-electron wave function is a little different things, right? Molecular orbital is intermediate concept. It is in between atomic orbitals and multi-electron wave function. But it is really useful concept for intuitive perception of the system. So if you look through the list of orbitals, you can see that each orbital has a number. And for this specific model, for this specific basis set, for this specific functional, the highest occupied molecular orbital has number 20, what? If I don't forget, let's look on the list of orbitals. So more, did it disconnect me? No. More E sub so we jump from occupied to unoccupied at number 24 and 25, right? So as we discussed a week ago, most interesting chemistry and most interesting optics, most interesting electric phenomena happen with involving these two orbitals. So they are critical for understanding properties of the system. And it would be really intuitive to draw them and see how they are distributed in space, right? So orbital 24 and orbital 25. It will be molecular orbitals composed as superposition of atomic orbitals. So it will be clouds in space. And for each orbital number, it will be a different figure. Let's get through practical steps how to draw it, how to get it. So if you look through this instruction file, you see, first there is a summary of this. There shouldn't be slash here. There is a summary of the steps, but they're really simple. You can look in your /bin advice MO. MO is for molecular orbital. So as far, oh, by the way, do not take literally. It is another common thing that may confuse several people. Do not take literally what is written here. The name of the argument is individual. It depends on how you named your files, right? So our style of thinking can be different. I tried to record the chemical composition, method of electronic structure, and basis set, but you can design it differently. So .chk is the service file that is not readable neither by humans nor by most of computer codes. It's a service file specifically for Gaussian. But it has encoded a lot of information, including molecular orbitals. We, as humans, like images. And there are several standard steps to convert this hidden information into standard images. So first, there is a step similar to de-archiving. It's not de-archiving. Do not tell it in public. But same as like if you have zip file, you unzip it. Here, form check, apply to this .chk, and then you repeat the name of file, but make point f chk. So there is no science behind it. It's just necessary step. Okay. And as soon as you complete it, make sure that you do not have any error messages. It will tell something pleasant, like complete, done, no complaints. Let's do it right away. So form check test CHK test FCHK. Enter. So nothing bad happens. It doesn't report errors. Some of you may develop question out of curiosity. Like, we know that the remote computer has installed Gaussian and Gauss view. What the heck are the form check and next command, kubegen? So, you know, packages, right? If you install software, it doesn't mean that it is consists of only one command. So Gaussian software automatically includes several executables that are automatically found through the correctly installed path, and form check is a natural part of Gaussian. So try to practice this form check, and then I will not make a circle because it should be simple. I'll make a circle in the next step, and then at the next line there is a command that converts let me give a little introduction of what we are doing, so that we get it a little better. Okay, let me attract your attention, especially like if you care only about pretty images, lean back and relax. But if you care about, I'm just jumping a little bit, putting car in front of a horse. It will be covered in the class. But in order to understand what we are doing, you may enjoy this little equation. So remember, yesterday in class, we discussed atomic orbitals, right? And the atomic orbitals are specified by quantum numbers, principal, magnetic, and orbital, right? But in addition, since we have many atoms, the set of orbitals will be specific for each atom. And these functions will depend not only on coordinate of electron, but coordinate of electron minus position of atom number I capital, right? So there is a set of atomic orbitals centered on each ion. Centered at nuclei number I. Make sense? Now, they all are added together, which is symbolized by the symbol sign. But there are so many molecular orbitals. And they all, as we will see in a few minutes, are different. So the atomic orbitals contribute to molecular orbital with different proportionality coefficients, different expansion coefficients, right? So we add together these functions with different expansion coefficients. And this expansion coefficients, it is what is saved in the form check files. Okay? And in about 2 weeks, we will learn how these proportionality coefficients are found. But we all love bubbles. We love, You don't? You don't, okay. Everyone except Queenie loves bubbles. Balloons, three-dimensional shapes, right? Orbitals. So three-dimensional shape, or more specifically isosurface of molecular orbitals, is what we are going to draw, is what is shown right here, right? So it's just one function of position. And this is obtained by adding together all atomic orbitals times expansion coefficients. The expansion coefficients are specific for each molecular orbital, right? So expansion coefficients are dictionary of converting atomic to molecular. And there are many of those. As many as atoms, as many of quantum states on each atom. Right? So we need a procedure that converts set of coefficients into three-dimensional shapes that we can draw. Again, going from discrete set of expansion coefficient to continuous three-dimensional function that we are going to draw here. And the command in the command line, this one, CHEM676, is implementation of this equation. So the word cube is used because the figure that we are going to draw in few minutes is represented by values of wave function at each point of space in a specific range of space, typically cubic. So many grid points in X, Y, and Z. So the word cube represents that it is often rectangular, and often with the same rectangular with the same sizes, which is a cube. Okay. CHEM676 space O, which stands for orbital, space MO equals 24, meaning that we do want highest occupied, which is 24 only for this system. When you will be practicing different systems, this number will be different. Space, then name of your fcheck file. Again, it is very unique for each of you. You name your files as you want. It's not, then space, and then you give, again, your creative name for the cube file. Like, I suggest molecular orbital number 24.cube. Okay? Let's practice this step. Yes, I will approach it in a second. So, more. And if my memory doesn't serve me well and I'm immediately forgetting what I've told, advice, molecular orbital. I do it here, I can just put it here. So CHEM676 space O, then MO equals 24 space FCHK space MO 24 or whatever I like dot cube. So this operation takes a little longer because it goes through each expansion coefficient and each point in space. But longer means for this small system like 20 seconds instead of 1. So let me make circle and check that you didn't get any errors. And next step is the most pleasant.
Uh-oh.
Okay, let's just copy the example
Okay, so after you complete this step, you should see that there is a file with extension cube. And the next step is the easiest and most pleasant. So you open Gauss View. There. In Gauss View, you are opening this cube file. So on the first glance, you will not see it because it has a filter for extensions. So check for extensions .cube. So you select file and open. After you open, you'll see only the model that also is discouraging for some of us. Like, what is my orbital? I want orbital, not the model. I have seen this model many times. I'm tired of it. So what do? You are go into your navigation tool and click onto results, which specifically has surface contours. So since you have already opened this file, it recognizes that you have opened this molecular orbital number 24, and here number of points 80, 80, 80. It means it shows how many grid points in x, y, and z direction. So 8 is 2 to the power 3, right? 8 to 8 cubed will be 2 to the power 9. 2 to the power 10 is about 1000. 2 to the power 9 is about 500. 10 by 10 by 10 is 1000. So it's about 500,000 grid points, right? And this grid point, remember last time in class we discussed isosurface, right? So the 500,000 grid points is possible. You can do scatter plot and put like clouds with denser points near the center where it's higher density and more sparse where they are less. But it is expensive numerically and hard for humans. Instead, one practices so-called isosurface. You remember it from yesterday, right? So, and before we draw, here, see ISO value for new surface, right? So it will, it instructs to plot continuous but curvilinear shape at any place where molecular orbital value equals 0.02. So it's like going in space. Is it 0.02? Yes, I'm going here. Is it, if it is bigger or smaller, it changes direction. And it covers areas of space. And surface action, new surface. Click, ready. Okay?
Yay!
And you may have some creativity to find ways to browse through menus and find ways to make it more visually appealing, like make this isosurface value transparent, or select different ISO values and inspect this. Let's redo it for larger ISO value.
What are the white circles?
Hydrogens. The circles are atoms, and this colored clouds are orbitals. So, by the way, based on your chemical background, so, and based on what is drawn here, so molecular orbital is composed of atomic orbitals on each atom. So, which of the atomic orbitals on which atoms contribute at most for this molecular orbital? We do not need any math or computational chemistry for this. It's like freshman chemistry question. Like rotate it and think. So do you have any noticeable on titanium? No. Do you have anything noticeable on hydrogen?
Yes.
No. No, not noticeable. But here, we do not see it right now, there is oxygen,
Oh. Yeah.
right? So there are orbitals on oxygen. Which shapes do they have? S, P, or D? P. So this molecular orbital is composed as superposition of P orbitals localized on 4 oxygens, right? Correct? If you are chemist in your heart, you should like celebrate it, like, oh, I've learned something. It's really important for analyzing. So why occupied orbitals are on oxygen? Not on hydrogen, not on titanium.
They have those smaller electrons.
Any? Yes, yes.
Oh.
So oxygen is oxidizing agent, high electronegativity. So it's like greedy person who tries to pull everything to itself. So oxygen does have electrons that it may be removed from other other elements, and therefore it is occupied. Okay? I'm going to make a circle. Please make a screenshot and save it, either in PowerPoint or in Word for your future homework, which will be formulated soon. If you are sure what is going on and how to do, please consider to draw 5 more orbitals for the same component. 5 unoccupied orbitals, which will be 25, 26, up to 30. And then try to analyze it for yourself in your head, and maybe on writing. Like for the highest occupied, the molecular orbital is composed of 4 oxygen p orbitals. Here is the question: which atomic orbitals compute at most to lowest unoccupied molecular orbital? We can write it down. Which atomic orbitals contribute most to lowest unoccupied molecular orbital? So if everything works, please try to answer this question, and I'll make a circle and check that.
Okay, so I need this for check thing. It seems like my F check file has nothing in it.
Yeah, this said 24, 25.
Yeah, okay, yeah, that's something. Let's just for trading. It's gonna be. You just next time we practice what should do. Just read these messages. So now you test check. Okay. Now let's go to this. a screenshot and put it in either Word or PowerPoint. Yes, yes, for PowerPoint. PowerPoint, yeah. Excellent. Which Orbital is this? Same as we do?
Yeah.
Oh, okay. Okay, so try to redo the smaller as a surface value, 0.06. Yep, yep.
Let me go back and click oh, get out of Gauss. Yeah, you're in something. Get the exit out of Gauss and edit that. Because that, well, what XGEM is like running Gauss, and that's all it's doing. Anything you're typing in.
Then go to after the journey, try to report other modules. You'll see things. Try to use larger number of tokens available. Because then it takes no space, but it will.
Look at this. Is this what you want? This literally.
Oh, you don't delete them, you take them out together.
This is really.
No,
This is- look at what I'm reading.
separate, separate image for each orbital.
I feel like I made Frankenstein. That's perfect. Excuse me, Frankenstein monster.
Yep. Yep, it's reasonable to use larger value, larger number of lines available. The definition is 0.02, maybe included 3 or 4 times. Okay, I'm going to do the same and try to put other orbitals.
Which orbitals did you want us to do again?
5 next,
Okay.
like 5 lowest unoccupied orbitals. Luma, Luma plus 1, plus 2, plus 3,
Gotcha.
plus 4.
Okay.
Did you get something like this? Try to use larger ISO value. So I put 0.08.
Rather than what, 0.1?
Huh? Just 0.1. The larger the number for ISO values, the more condensed bubbles you will have near the atoms. You do not stop those here. Oh, by the way,
When you say 0.1, at what point does it even put small and stuff?
That's not very defined on this way. Wait, yeah.
which one? Yeah, 5 it will be orbit. Try 25 or this should be
Mary, so,
Yes.
do you want me to get that orbital on there?
Yes, okay, so I didn't do this because my check files are really messed up, but did you make your orbital for it?
Yeah,
You did, okay, here. Let me go to your terminal.
So,
I could do it without even Okay. So you're in the gas feed? Okay. So you're right. Okay, so. You made a good guy?
I'm all 24.
So it opens up, you don't see anything that's okay. So you go to the results, you see this guy's kind of six space and it tells you different place. So the surface action is the surface. And it's great. You got this going on.
Do not do more than 5.
So this is the guy you made, and this is, you just have to show on your surface. So when you make demo 23 or
Do you always want 20? Why?
so you can save each of these and show them in a beautiful carpet.
Okay, so just like modify that MO for
It's not a magic value.
and save it as a new cube file.
Yeah, well, no, just,
You just want us to be consistent on the ones that we open. So all of us do 20.
It's better.
Okay, so I'm gonna have to save, I just have to modify this.
Yeah.
I'll get a new
If it's
photo
more
like
for
on the screen there, and then just do a screenshot, put it in a PowerPoint.
That's really.
Got it.
You're welcome. And I think when, now, if I remember correctly, once you generate more, you're gonna have a list here.
Okay.
And you just pick the right one, if I remember, but I might be wrong.
Okay.
There's a few ways, there's like one way to do that, so.
Yes. Do not keep so many orbitals in one image. Let me show when you control orbitals, when you in this menu. Here. You see, I have only one, but if I click surface action, I can do new surface again and again, and it will pop up this list, and they will interlace with each other and interfere our understanding. Open new window if you want to see several orbitals. It's a little too much to have more than one orbital in one.
Deep in the memory is recalling that you can have multiple cubes available, so you're gonna.
Oh, yes.
That list is gonna get.
Oh yes.
Okay.
And I'm not lying. I'm not doing bad things intentionally. But this cube gen and molecular orbital generation can be done by mouse-operated commands.
Yeah.
Just we do not need to rush. We better do slowly but surely with understanding what is going on. So did you get images like this? Please lift hands who got unoccupied orbitals similar to this one. Okay.
My check file is bad, so I can just.
Copy the one from me or from.
Oh, okay, sure.
Don't waste time. Who didn't get similar? One?
I'm still trying to figure it out.
Okay. One. Who else? Okay. I'll make a circle. So it is 24, right? Let's do 25. Oh, you didn't prepare yet. Let's open another.
Typed in a 0. Yeah. Yeah.
That's really good.
As a service. Larger value, more condensed images. Can you unoccupied areas?
Yes.
Okay.
Well, look,
Do they look
here,
like
man. You're right.
Yes. You're fine? Anyone else who didn't get the orbitals? Oh, you're doing machine break? No. You can do it without noting. You need to put this shift cell 100%. Or you need another
So everyone got these orbitals, right? Now let's come. Remember, in class we were looking on the P table for atomic orbitals, right? Let's go to P table once again. Select titanium and look for these 3D orbitals. So one of them look this way. So it is 3D dz square orbital with zero projection of magnetic quantum number, right? And if you tried to explore other than 20 orbitals, rather other than 25, if you tried like molecular orbital 27 or 26, you will get something similar to different other d orbitals localized on titanium. So the answer on question that lowest unoccupied molecular orbital for this system is localized on titanium ion and has 3D character, right? So this orbital, lowest unoccupied, is empty, lowest unoccupied. So there is no electron. Although natural metallic titanium has some 3D orbitals occupied. What does it mean? It means that our greedy man, hungry oxygen, removes electron from titanium and puts it on yourself, right? On its own O2p orbitals, right? So it removes electron from 3D and place it on 2D. And if you have not the hydroxide but oxide, then you have network of titanium and oxygen. Each oxygen removes something from titanium. Make sense? Okay, so I think it is enough for instruction, but let me invite you to complete this additional 5 orbitals. So there are 5 3D orbitals, and if you look through orbital number 25, 26, 27, 28, 29, they all should are expected to have 3D character. They will be not pure, because it is admixture of all orbitals. But the major contribution will be from titanium 3D. Please do not forget to screenshot it and put it in your reports. Okay? I'll stay here a little bit more time and make circles, checking that you feel comfortable on building these 2 other models. So titanium hydroxide dimer should be really simple. I have no doubts that you will do it. But this one, cesium-4 lead bromine 6, is a little smaller, but it is more challenging.
I don't think I did that one right.
Okay, I'll make this. If you are in rush, if you have other activities or other classes with homework, do not waste your time. The formal part of the meeting is done. I'll just go around and make sure that you are feeling comfortable with drawing these structures for the expected homework.
Why?
Huh?
So why exactly are you saying that specifically 3D is what, like you said, to answering our question, which atomic orbital contributes more? Why is it 3D exactly? Just because we're comparing the two and they look like each other?
Yes, yes, it is. We do compare computed visual appearance of computed molecular orbitals and visual appearance of atomic orbitals that are aware for us, right? So we do it at the intuitive and visual level,
Okay.
right? If you would need to dig deeper for as a major point of a thesis, we would look inside into like form check, or we'll find way to print out these coefficients and find which of the coefficients has larger value. But right now it is not needed. Okay?
Perfect, yep, thank you.
Yes.
I think mine's wrong. There should be, those should be swapped, right? Like
So,
oxygen's here, or kind of?
each the lead has chemical bond. You can draw a chemical bond to each of the bromines.
Oh, so it's
The
gonna.
bromines, but cesium shouldn't be connected to anything. It should float around.
Oh, okay,
freely.
okay, I get it. So it's gonna be. Okay, got it.
Well, I
Yep,
got the
yep.
Don't worry, man.
I'll probably just try to draw it myself.
I think I can use this. That makes sense, yeah.
The issue is we're like right on the edge of our shooting. I know by the end of the semester we're gonna be like, this was a great. I know we're gonna say. Okay, make sure you send us an email now. It's gonna be last.
You're faster. I'm trying to keep up with you.
I don't know why we're doing this.
What's on the board is going to be the
Huh?
assignment, right? What we have on the board is going to be the assignment.
Yes.
Okay.
Yes.
Yeah, just see the pictures from the different, naming them like different, like how I, what like. Yeah.
What's that? I don't know why you're saying it's hard.
Good night.
Do you know of any books that actually go into the theory of the Peltier effect and the Seebeck?
Which effect?
Peltier effect and Seebeck effect?
I'll look and suggest. There are a couple.
Because these are currently the most efficient models that I can find. I thought I'd actually just get one so I can play with it a bit, but
Okay.
I don't know. It's just it's confusing because both the NMP materials are all just gained in series,
Mm-hmm.
and then magically once it gets hot, once it gets cold. So even though the NMP materials aren't actually separated, it's not N materials on the cold side, NMP materials on the hot side. It's actually the junction between the NMP materials, which has led, I don't exactly fully understand how it works, but I know that it does work.
Your words are music for my ears.
Okay.
We'll discuss it more, and I think it will be a great project, and
Okay.
it may lead into something much bigger than just a project.
Okay, okay. And like I said, the current, like the efficiencies of this device is like around 7%. And getting anything higher, you start getting into really theoretical type ones. But alrighty.
So just anywhere on the outside? Because I have.
Right now.
And I think it's